Okay, so here's a question for you. Have you ever just stopped and wondered why the universe bothers making, well, interesting stuff? Like galaxies and life and us. It seems to start out super simple, then it gets incredibly complex, and then the story goes it's all supposed to just fade away into a boring, uniform soup. So, why the complicated middle part? Let's get into it because it turns out there might be a whole new kind of law governing everything.
And it all starts right here in a cup of coffee. We've all done this a million times, right? You start with two totally separate, orderly things, the black coffee, the white cream. That's a very simple state. Then you pour, and for a moment, you get these incredible, beautiful, complex swirls. That's peak interestingness. But if you just wait a little bit longer, it all just blends together into a single, uniform brown liquid. And we're back to simple again.
And this right here, this is the heart of the puzzle. Now, physics has a famous rule that says disorder, what scientists call entropy, that's the blue line. It's a one-way street. It only ever goes up. The universe is always getting messier. But what we feel, what we see in that coffee cup is that complexity, that's the red line. It does something different. It goes up, it peaks, and then it comes back down. It has a story, a beginning, a middle, and an end.
And look, this isn't just about your morning brew. This is a huge question that physicists like Sean Carroll are asking about the entire universe. It starts out as this simple primordial soup, and it's supposed to end as a simple spread-out heat death. But in between all that, we get everything. All the stars, planets, life, all the interesting stuff. So why this arc? Why does the universe get more complex before it gets simple?
So you'd think the most famous law in physics would have the answer, right? Well, it turns out entropy just isn't the whole story. Not even close.
Yeah, the usual suspect is this guy, the second law of thermodynamics. It's this ironclad rule that basically says things get messy over time. It's why an egg will never unscramble itself, and it's why your room, left to its own devices, trends towards chaos.
And hey, to be fair, the second law does a fantastic job of explaining the end of the story. It tells us exactly why the coffee and cream end up in that uniform brown state. That's the messiest, most disordered, highest entropy state it can possibly be in. It's the final destination.
But here's the thing, the second law is completely silent about the journey. It tells us absolutely nothing about those beautiful swirls, those complex tendrils, the most interesting part of the whole process. It only sees the final mess. So to understand complexity, we gotta look somewhere else entirely.
And that somewhere else, believe it or not, isn't in physics, it's in computer science. And this is where things get really, really cool.
Let's just try to reframe the entire problem. What if we stop looking at the state of the coffee cup, or even the universe, as a bunch of particles, and start looking at it as a string of data? Like a giant file full of ones and zeros? How would a computer even begin to describe that file?
This brings us to this amazing, mind-bending idea called Kolmogorov complexity. It's actually pretty simple at its core. The complexity of anything is just the length of the shortest possible computer program you can write to generate it. Seriously, think of it as the ultimate zip file. The smaller you can compress something, the simpler it truly is.
And this makes perfect sense when you see an example. So take a simple string like 0101011010. The program to make that is tiny, right? You just say print 01 5 times. Easy. But now look at a truly random string of letters and numbers. There's no pattern. So the only way to describe it is to literally just write out the whole thing. It's incompressible. And that means it has maximum Kolmogorov complexity.
Okay, but hold on. This creates a brand new problem. Does that mean a screen full of random TV static is the most complex thing imaginable? Even the guy who invented the concept didn't think so.
Yeah, the great mathematician Andrei Kolmogorov himself pointed out this exact flaw. He said, sure, a random string is maxed out on Kolmogorov complexity, but it's also about the most boring, least interesting thing you can possibly imagine. It has no structure, no pattern, nothing. It's just noise.
So we need a smarter definition. Instead of trying to describe the raw data, what if we try to describe the model that generates the data? This is an idea called sophistication, or a cooler name for it is complexotrophy. We're not trying to zip the file anymore. We're trying to find the shortest program that explains the structure inside the file.
So let's take this new idea for a spin with our coffee cup. How does it do? Well, the initial state, that is a really simple model. Top layer is cream, bottom is coffee. That's low complextropy. And the final state, it also has a simple model. Just place all the particles randomly. Also low complextropy. But that middle state? Oh, the model for those swirls? You need a really long, complicated program to describe all those boundaries and shapes. That's high complextropy. See, it works. It actually matches our intuition perfectly.
We are so close. This complex entropy idea feels right, doesn't it? It seems to perfectly capture what we mean by interesting. But there's just one last, really clever wrinkle we need to iron out before we can actually propose a new law of nature.
Okay, so here's the catch. A computer scientist named Scott Aronson pointed this out. If a system follows predictable laws of physics, a computer could always cheat. It could just say, here are the simple starting conditions, now run the simulation for 10 seconds. That's always a super short program. And it means the complexotropy would never really go up, which we know isn't right. And the solution is actually brilliant. You add a deadline. The program doesn't just have to be short, it also has to run fast. Simulating everything from the beginning might be a short program to write, but it takes a long time to execute. A truly efficient program would have to describe the structure directly, and that's what makes it complex.
And all of that brings us here, to this grand idea, a conjecture for the first law of complexodynamics. It says that the complexotropy of a system, defined as the shortest and fastest program that can describe its structure, will naturally follow that curve we saw at the beginning. It will rise, and then it will fall.
Okay, so this is a super fascinating idea about physics and information theory. But why does this matter to you right now? Well, because this exact way of thinking, it is the secret sauce behind the entire AI revolution that is completely changing our world. Seriously, just think for a second about what an AI model like ChatGPT actually does. You feed it a mountain of incredibly complex data, the entire internet basically, and its whole job is to find the simplest, most efficient model that can explain all that data. It is literally searching for complexitropy. It's hunting for the simple rules that generate our complex world.
And this suggests something really profound. It suggests that the tools we invented to make sense of information might be more than just tools. They might actually be a reflection of how reality itself works. That maybe the universe isn't just evolving according to the laws of physics, but also according to the laws of computation.
Which leaves us with one last absolutely massive question to chew on. If the rise and fall of all the complexity around us, from coffee cups to galaxies, is governed by a search for the most efficient description, does that mean the universe itself is performing some kind of computation? Is reality just a program that we're only now beginning to understand?